Hello, in this presentation I would like to talk about multi-index Monte Carlo methods for PDEs with random coefficients. This is a recent joint work with Michael Feischl from TU Vienna and Christoph Schwab from ETH Zurich. Before I start, let me thank the organizers, Cody Law, Fabio Nobile, Rob Scheichel and Karen Wilcox for putting together this online conference. It's really exciting. I've never joined an online conference and see how it goes. I'm sure it will be a great meeting. So this area of PDEs with random coefficients has grown a lot over the last few years, and you can see here I've listed some names who have contributed to this area. It's really exciting to be part of this. And in my talk today, I would like to focus on the multi-index Monte Carlo method applied to a simple setting of PDEs with random coefficients. So this is this classical setting of a diffusion equation with zero boundary conditions. And let's say we have a Lipschitz domain D in RD. This in the sequence Y are the random coefficients, and we assume that this diffusion coefficient is given by this infinite expansion, and there's a number of assumptions which go into it. I'm not listing all of them, but one assumption which goes into is that the A of xy is bounded from below and from above. Now, these functions psi j are important. We define the coefficients beta j here as the infinity norm, so we assume that the infinity norm of the psi j is bounded. We also assume that those betas are ordered in a decreasing order, and we assume that this infinite sum of the beta j to some power p, where p is between some value between 0 and 1, is finite. And that guarantees that this sum converges for all x. And it also tells us in some sense how fast this sum is converging. Now, the goal is to approximate a linear functional of the solution u. So u is the solution of this PDE for some given right-hand side. And we want to, for instance, approximate the expected value, which I can write here as this infinite dimensional integral, and which we write here as this limit of the dimension going to infinity, where this is is just a truncated integral which we truncate after s terms. Now, the first methods discussing this type of problems were based on the following idea. So here we have the exact value, and this is an approximation. And in fact, what this is we replace the integral with a quadrature rule. So in the setting I'm discussing here, we just take the average over some sample values. The g is the linear functional, and the UHS. The H means we use a finite element approximation, and S means we truncate this infinite sum given here. We truncate this infinite sum after S terms. So when we do this, we can plug this into our PDE and use a finite element solver with mesh width h to obtain an approximation of this solution. And this we can plug into this type of algorithm here. And I'm in particular interested in the Monte Carlo approximation, where these points Syn, so these are S-dimensional vectors, they are IID uniform points in this cube from -1/2 to +1/2 to the power of S. So as we have seen, the error is of this form here, and using adding and subtracting some terms, and using the triangular inequality, we obtain these three terms, where the first term is the truncation error. It's just the exact value minus the solution of the PDE, where we truncate the random coefficients after S terms. The second is the finite element error. So after truncating, we have here the solution of the truncated problem. We use the finite element method to approximate the exact solution. That gives us another error. That's the finite element error. And finally, the last term is where we approximate the exact integral with a Monte Carlo rule in our case. Now, if we want to obtain a good approximation, if we want to make the error here small, then what we need to do in this situation is that all three errors become small. We need to make the truncation error smaller by increasing S. We need to make the finite element error smaller by decreasing the finite element mesh width. And we also need to decrease the integration error by using more sample points. It doesn't make sense, of course, to just reduce one of the errors, say to reduce the truncation error, leaving the others to the same, because then that does not guarantee us that the error becomes smaller and smaller. So this sum of the three error terms forces us to balance all those three errors in some reasonable way. So ideally, it would of course be much better if we would not have a sum here, but a product of those three error terms. Now that can of course not be true, because that would mean we could just increase the truncation dimension and the error would become smaller and smaller. And that can obviously not be true. But the question is, can we do something which in some sense resembles this? And the answer turns out to be yes, in a certain sense, which I discuss in the following. And the idea comes from this Multi-Index Monte Carlo, which was first published in a paper by Hattiali, Fabio Nobile, and Raul Tempone in 2016. So this is an extension of this idea of multi-level Monte Carlo, which comes from Mike Charles and Stefan Heinrich. And the multi-level Monte Carlo method has been applied in a number of papers, also in connection with quasi-Monte Carlo methods. You can see here a number of papers. The multi-index Monte Carlo has now been used in many papers as well. I'll just point out two papers here. The first one, Robert Nuance van de Walle, they use multi-index quasi-Monte Carlo. And there's another paper by Reisinger and Wang, where they obtained convergence rates for a multi-index Monte Carlo method, but for not the same problem as I'm discussing in this talk, but for a quite different equation. So there was an open question of, can we actually obtain convergence rates for this multi-index Monte Carlo for the setting I'm discussing here. To introduce the general idea of multi-index Monte Carlo, let me do this in some abstract way for the moment. So let's say we have a sequence N1 smaller than n2, smaller than n3, and so on. Another sequence of decreasing values, decreasing real numbers, h1, h2, h3, and a third sequence which is increasing, namely s1 smaller than s2, smaller than s3, and so on. Using the sequence, we define a sequence of quadrature roots, qk, with each having nk points, a sequence of finite element projections using, say, 1 over hj elements, and a sequence of truncation dimensions si. And I'm thinking of those three, qk, pj, and ti, now as operators applied to the right-hand side in our PDE. So we have our PDE here. Here is the right-hand side function f, which is in h minus 1. And we apply these operators to this function f here, which gives us then the solution of this PDE u. So for instance, if we apply pj, ti, and qk to the function f, then that is just a quadrature rule with nk points, where the PDE problem has been truncated after SI terms, and we use a finite element method with where the mesh width is hj. So now with these parameters increasing and decreasing, as shown here, we see that we can write the exact solution as this triple sum here of these operators as it is outlined here. We assume that Q0, T0, and P0 are all 0. And so this is a telescoping sum. And this is just the limit where QK, TI, and PJ go to infinity, and we obtain the exact value in this way. So now, if we want to obtain an approximation, what we can do is we truncate this sum, this triple sum here, to have a finite sum, and we can calculate these terms then using some algorithm. Now, there's different ways of how this sum can be truncated. One way is where we sum I, j, k. Each of those indices goes from 1 to L. And then we can see that we can simplify this expression here, and it just turns into QL, TL, and PL applied to the right-hand side F. And this is just the single level method which I mentioned at the beginning. Now we can also truncate this infinite triple sum in a different way, namely the following. We have ijk in n, and such that the sum of I plus j plus k is small equal to sum L. And this type of sum here can be simplified a bit further, namely we get this expression here. Now, this is our multi-index algorithm now. So this sum here, of course, is now different from what we had here in the single level, and there are certain benefits in doing it in this way. One thing to notice here is, as when the index increases, so say if the index k increases, then also the computational cost increases of computing qk. And the same applies to the other operators. Ti, when I is large, then there's a higher cost associated with computing with Ti, and the same with Pj. And one thing what is happening here is we avoid this case where all indices I, j, and k are all large simultaneously, because this restriction excludes this case. And so that is a large savings in terms of computational cost compared to this single level algorithm here. Now for the error, so we have here the absolute value of the difference of the exact value and our algorithm. We can just apply the triangular inequality here. So the error, the I minus our algorithm, is just the sum over the ij k's in n, where the I plus j plus k is bigger than L. And then applying the triangular inequality, we in fact get this term here. And here we just have the error terms where I plus j plus k is bigger than L. Now we want to balance the errors with the computational cost. And so for some particular finite element methods, without going into the details, for instance, we have a cost of h to the minus t and an error h squared. For the Monte Carlo methods, if we use endpoints, we get an error of the order n to the minus 1/2. And for the truncation, it turns out that the cost multiplies with a factor of s, and the truncation error associated is of this form here, s to the minus 2, 1 over p minus 1. And that comes from some well-known paper from Cohen, DeVoe, and Schwab. Now, to make this error small and to get an improvement of the cost versus the error, one needs to show that the errors here in fact multiply. And if you think back of the case where I talked at the beginning earlier of the error for the single level case, we had the sum of each of the terms, and ideally we wanted to have a product. And that's exactly what we are aiming for this expression here. We don't want the error to be a sum of the errors arising from those operators q, t, and p, but we want it to be of product form. So we want to have that the error is just a product of the three terms arising here with the appropriate indices k, I, and j. So we want to prove an error of this form here. And in this case, this can of course be true, because if I have, for instance, if I would have qk minus 1, if they both are the same, so if I replace the k minus 1 here with k, then of course I would get 0, and the same also for the other two operators. But it turns out that proving a bound of this form turned out to be quite tricky. But I will get back to that a bit later. So now, let's say we have such a bound, and we can say analyze the error, what's happening. So we have, say, hj of the form 2 to the minus j, the nk says 2 to the 4k, and si shall be of this form here. Then the error of our algorithm is bounded by this sum here. I just substituted the previous bound in the expression before. So I just substituted this bound here in the expression for the error here. So then we obtain then an error of this form here, where the sum is over I plus j plus k bigger than L. And we can simplify this expression. You can see here the particular choice of hj and k and si was to make this sum as simple as possible, and one can check that now the error is bounded by a term which is of the form 2 to the minus 2 capital L times L plus 1 squared. And so if we increase this capital L, the error of our algorithm in fact becomes smaller and smaller and goes to 0. Now for the cost, using again the values in the table here, we obtain that the cost using the algorithm AL is of this form here. You can see here the cost of each of the terms multiplies. So if we use, when we calculate this term here, then the total cost of this algorithm is just the cost of using QK times the cost of TI and times the cost associated with the PJ. And so we get that the error is of this product form here. However, when we calculate the sum of these products, it turns out that this is bounded by 2 to the L times the maximum of those three expressions. And you can see that the D here is associated with the finite element error. The 4 here comes from here, is associated with the Monte Carlo error, and this term here, P divided by 1 minus P, is associated with the truncation error here. And so here we don't have a sum of those terms, we just take the maximum. Now if we were to use the single level Monte Carlo approach, it turns out that the error is of the form 2 to the minus 2L. So it's very similar to the error which we have for the multi-index Monte Carlo method. However, in this case, the cost multiplies. So in the exponent here, we have the sum, whereas in the exponent for the multi-index Monte Carlo, we take the maximum of those 4 terms. So how can we prove this bound, which is of the correct order? So first we need to become clear of what we actually mean with these operators. We need to fill in some details here. So we have this operator Ti minus 1 and Pj minus 1. And so Ti Pj applied to the right-hand side f just means that we apply a finite element solver to the PDE where we truncate the random coefficients after SI terms. And the solution of this PDE is just denoted here by UHJ, and we use a coefficient which we truncate after SI terms. And to shorten the notation, I just write SIJF here. Now, the finite element method, we can first write the weak formulation. We define a bilinear form of defined as it is here, where we have the diffusion coefficient A here. Now there's a number of assumptions which we need to make for the solution to be unique and to exist and be unique. I'm not listing all these assumptions here. You can find them in the paper, but for instance, we assume uniform ellipticity and continuity of the bilinear form. Then we have the weak formulation of the problem, namely the bilinear form evaluated U and V should be equal to the inner product of F with V for all V in this space H H01D. To obtain an approximation of this solution, what we do is we define a sequence of finite element spaces, denoted here by this XHJ, which are subsets of H01D, which are increasing. So that means we use finer and finer mesh width, and they should satisfy a certain approximation property. And then we obtain a Galerkin approximation UHJ of our solution, where we replace the V. Now we restrict it to a subset of the space H01D, namely this finite element space. And we want to have this equality almost surely. So for almost all random coefficients y, which go into this diffusion coefficient a here. So the bilinear form here, it's not written here explicitly, but depends on the these coefficients y, and therefore also our solution depends on these random coefficients y. So now we have a finite element approximation, and of course we can define this finite element approximation, this Galerkin approximation, in the same way when we replace the diffusion coefficient A with a truncated coefficient where we truncate after SI terms. And then this Galerkin approximation can be computed on explicitly. So now for this difference of differences of these operators, we need to obtain a bound which is of product form. And it's not quite so easy to see how we can obtain a bound of this form. So we defined this Sij of f, this solution operator, given by this finite element solution of the truncated problem. So we truncate the diffusion coefficient of the SI terms. So we can write this difference of these operators as Sij minus Si minus 1j, and we subtract the Sij minus 1 minus Si minus 1j minus 1. And so here we have a difference of differences. We have the finite element approximation where we add two different truncation dimensions, and the same here, but we use a coarser mesh in this side here. Now, to simplify this, we need to define this inverse operator, which is from this finite element space xhj to the space h minus 1d, which is the dual space to this space h01d, and it's defined in this form here. So for each u in the finite element space, this inverse operator is given by the bilinear form where we use the truncated diffusion coefficient and defined for all v in h01d. So it's a functional defined on this space h01d because it's so it's in the dual space. And so in order to obtain a bound of this product form, what we do is we rewrite this expression in two terms here. One is now of product form. We have this difference operator where we have the same truncation dimension and but different finite element mesh width. Then we have this inverse operator, and then we have another difference of solution operators where we change the truncation dimension, but the finite element mesh width is the same. And it turns out for this expression here, we can indeed obtain a bound of product form. And we have some second term here, this error term here, which turns out we can also obtain an error bound of the correct order. So with this, we can obtain a bound on the linear of the absolute value of the linear functional of this difference of differences. And it turns out it's of the order which we wanted. So that means it's quite technical to obtain a bound of this form, but it means that we finally get the error bound which we wanted, which is of this form here. The third part here, the Monte Carlo, is much easier to estimate because the bound on the solution operator here just goes into the variance of our integrand. And we can use standard bounds on Monte Carlo errors to get the bound of this product form here. And so we obtain this bound of product form which we wanted, and we obtain this improvement of the error for multi-index. So the error versus work for the multi-index compared to the single-level multi-level method, single-level Monte Carlo method, I should say. We also performed some numerical experiments. So we have here a simple example where we have a square domain. The random diffusion coefficient is given by this expression here. We choose some right-hand side function f here of this form and use some finite element mesh width illustrated here, and the linear functional GU, which is just the integral over part of the domain. And we see that the error versus work converges with the correct order here, which corresponds to our theoretical results. So we have seen that we can in fact obtain an improvement, a proof which we can also show in theory over a multi-level method using the single-level approach. And in a number of cases, this also improves upon the multi-level Monte Carlo approach. An interesting extension, which we have not done in this work, is to also obtain analog results for quasi-Monte Carlo methods. This would require some further estimations because quasi-Monte Carlo methods require some smoothness of the integrand, and so one needs to have this bound of product form here for quasi-Monte Carlo, and to do that we also need to have a bound on the derivatives with respect to those random coefficients. So this requires an extension of the bounds which we obtained here, not just for this case, but also where we have partial derivatives with respect to the random coefficients here. And so this would certainly require some more work to obtain bounds of this form here. So with this, I thank you and come to the end of my talk.